Previous meetings, I showed you how rank dependence can be used to capture empirical phenomena. We started with hypothetical ones, so you get used to the formula. Then more empirically realistic and more important phenomena were considered. We will continue doing that today. We will be using rank dependence to analyze the experiment that we did. As you see, I'm spending quite some time on teaching you how rank dependence works. One thing, it's a sort of new animal. It's a mathematics that we hadn't seen in classical courses, so we have to get used to it. And also, it delivers everything that the behavioral approach wants. It can capture psychologically realistic phenomena. It can give tractable formulas that nicely captured, homeomorphic, if you remember. So those are all good things. Well, there are other behavioral techniques besides rank dependence for risk, but I think rank dependence is the best for risk. It's the most popular approach used now. It was a prospect theory user that got a Nobel Prize for it, so it's really a good thing to study. And also in the beginning of this course, I told you I have bigger ambitions with this course. In this course, I'm showing you in depth how the behavioral approach works for decision under risk. So you really see, I like that you get the feeling how psychological realism and mathematical tractability come together to improve economics. That's what we're doing now. But once you saw that for one field, I think if you work in other fields, if you work intertemporal choice, maybe behavioral finance or game theory, whatever, then also it's more easy to apply and even to develop those techniques once you know how it works. So I have many ambitions here. Today, other things that we will do besides the experiment is I'll introduce parametric families for probability weighting functions so that you can easily do calculations with them. I will define index, for the index of pessimism. So if you want to do regressions and see how much pessimism is impacting all kind of things that interest you, then you can easily do it. One thing that I will not do in the rest of this course, although it is important, that is preference foundations. First two meetings, we saw two classical famous preference foundations. I told you about every theory should have them. Well, surely rank-dependent utility has preference foundation, I can reassure you. And also the other theories that will be introduced later, they have them. They are available in the book, but because we don't have time to do very much, so there will be no more preference foundations in this course. So as I told you, now we're going to analyze the experiment again, now using rank-dependent utility. That's in a way a nicer thing because rank-dependent utility is more empirically realistic. We already saw expected utility is quite violated, but rank-dependent utility is better. Well, here I put up the stimuli that we used to measure the first two questions, alpha 1, alpha 2, you remember. Those were the questions. And now a problem is that in this experiment, we were not assuming known probabilities. We had candidate 1 and 2, a bit of a story, but there were no probabilities giving of the candidates winning. However, so far I only explained rank-dependent utility to you for the case of known probabilities. Unknown probabilities will come later meeting, but not today. Therefore, to be able to use the theory, we're going to assume now that in the experiment there were in fact known probabilities and they were 0.5. So both candidates had a 0.5 probability of winning the elections. That's assumed from now on. And with that understood, so here I write it again, it means we have decision making under risk, DUR abbreviated. We have probability distributions over money and preference over them. That's what we're analyzing now. We're using rank dependent to analyze it. I put the probabilities half in the figure, and with all of this, now I come to the exercise that I asked you to work on. We're going to assume that utility alpha 0 is 0, utility alpha 1 is 1 over 4. Under expected utility, you saw that we can always do that. And now you take my word for it that we can do it here also. So this is just assumed. And I ask you, can you find out something about utility alpha 2? What can you find out about it? The unexpected utility, we already saw it, it must be half. But now, other more general theory, rank-dependent utility, you don't know. So your exercise to come now is to find out what utility of alpha 2 is. And if you can do it, it may be nice to immediately continue with a follow-up exercise for alpha 3 and alpha 4. Also find out what you can about their utilities. Now put up here the stimuli that we use. The candidates are replaced by probabilities. So these are the stimuli. And then you can work on it and you can pause the video and do. And if it's nicest if you can find about all the alphas what the utilities are. If you find it difficult, I'll show next for alpha 2, then you have another chance to work on alpha 3 and alpha 4. But the nicest thing is if you can find out about all the alphas right now yourself. So work on that, and when you're done, come back. So I'm assuming that you're done now. So I show you the solution that I have in mind. And here I repeat briefly the two figures, small. I did not write the probability half, but you remember. Now, first I'm going to repeat the calculation that we did with expected utility. Well, then we had unknown probability P1, P2. Now we have probability half, but other than that, all the same. So we looked at the indifference in figure A, and we said those two must have the same expected utility. Here we go, this is the expected utility, left prospect, right prospect, they must be the same. We moved alpha 0 to the left, we moved 1 to the right, we got that equality. We did similar things for figure B, and you remember it all. And then we said, hey, this is nice, the right-hand sides of those two equalities are the same. Then the left-hand sides must be the same. Then the probability half of it was P1, but whatever it is, the probability is cancelling. So we concluded utility alpha 2 minus utility alpha 1 is utility alpha 1 minus utility alpha 0. And from that, we concluded utility alpha 2 must be half. That we did for expected utility. Now we have to modify that, generalize it to rank-dependent utility. So now if we look at the indifference in figure A, we must say the rank-dependent utility of this lot 3 is equal to the rank-dependent utility of that. So we have to write here the rank-dependent utility value of the lot 3. Okay, we do it, and always we see you rank the outcomes, Alpha 1 is the best outcome. So under rank-dependent utility, we transform the probability of the best outcome. We take the W of half. The remaining weight, 1 minus W half, goes to utility of the best outcome. So here we wrote the rank-dependent utility of the left prospect. And a similar story for the right prospect. You remember alpha 0 was 10, it's bigger than 8. So alpha 0 is the best outcome. We take the W transform of the probability. The remainder of the decision weight goes to the utility of 8, and we get this equality. This is the equality that we get from rank-dependent utility. Those two prospects have the same rank-dependent utility value. Again, I can move alpha 0 to the left, and I can move 1 to the right. And now this is what we get, is the expected utility formula, but with the brown things added. I can do the same thing in figure B, and I quickly show it because you know how it goes. So here is the rank-dependent utility equality that we get from figure B. Move alpha 1 to the left, move 1 to the right. And without the brown on the expected utility, we saw that the right-hand sides were the same. Now with the brown added, what we have on the rank-dependent utility, still we can see that the right-hand sides are the same. So still we can say that the left-hand sides must be the same. And before the probability P1 or half was cancelling, but now we have the W of half, it's unknown, but it still cancels. So also on the rank-dependent utility, we conclude utility alpha 2 minus utility alpha 1 is utility alpha 1 minus utility alpha 0. So it remains the same as expected utility. And this extra function W coming in doesn't really change things in an essential manner here for what we're doing here. We can still conclude utility of alpha 2 must be 2 over 4. That also holds if you did as if rank-dependent utility in the experiment. Now, if you like to work more on alpha 3 and alpha 4, you can pause the video and work more on it. And then okay, I'm assuming you're done. So you came back. Then I show you alpha 3 and alpha 4. And of course, they have quite the same mathematics. Here it is a figure C I bring in that give you alpha 3. Then here is, I just immediately write, without the brown was the expected utility that you already saw. The brown adding of rank-dependent utility, you know how it goes, the same as we saw before. This is in fact all the same formula as we saw before, only with the alpha, the superscript increase all by 1. We still have the same right-hand side, left-hand side. We conclude utility alpha 3 minus utility alpha 2 is utility alpha 2 minus utility alpha 1, the same as we had with expected utility. Utility alpha 3 is 3 over 4. And of course, one more time the story with the alpha 4. Maybe it gets boring to you now. All the same story. Again, utility, all the alphas are equally spaced. Utility unit, utility alpha 4 is 4 over 4 is 1. So we conclude under rank-dependent utility, the alpha are still equally spaced in utility units. We can still set utility alpha j equal to j over 4. That means that this measurement method that we used under expected utility is robust against violations of expected utility. It continues to hold even if it's violated. Also, you may remember that when we had only done expected utility, you drew the graph of your utility function using your alphas. Then later you heard expected utility is violated, and then maybe you thought, oh, that graph was a waste of time. Now you see, no, it was not. That graph remains valid. It is also the graph of your utility function, the rank-dependent utility. And also, you may see, when you first see rank-dependent utility formula with the W function, you found many unknowns. You think it must be very hard in this theory to measure the primitives of that theory. But now you see that despite the big generality of the theory, still measuring utility is not so difficult. In fact, we already did it in the experiment. We have already been measuring utility and the rank-dependent utility in the experiment. So this is not as difficult as people thought when they first introduced rank-dependent utility. We're going to analyze the rest of the experiment, but that will be in next recordings.